first clean up the input curves. Different from previous methods, we don't directly match the input curves or modify the curvature of input curves. The cleanup here is more like a preprocessing that only marks and determines which part of the input curves we should try to exactly preserve. Exactly preserving everything is not practical because the input could be problematic. After the preprocessing, we first generate a linear mesh with constraints on boundary edges and boundary vertices for easier curving the mesh later, and then we improve and curve it to generate a valid and high-quality output mesh. This is different from other methods. While most methods also first generate a linear mesh and then curve it, their linear mesh are not generated in a way for facilitating the later curving. Now let me introduce our algorithm in more details. Our input are Bezier curves, which will be separated into primary features and secondary features. I'll talk about the separation soon. Our output is a curved triangle mesh that conforms to primary features and approximates secondary features up to epsilon. The first step of our pipeline is high curvature and inflection point separation. Note that the separation here only separate the range of parametric values, but does not change the control points of curves. And in this step, we first cut the curves at inflection point, marked in black on the right. This is for easier curvature computation, which will be frequently used in later steps, because in this way, the curvature of all curves would be monotone. And then we cut the curves at high curvature points, for example, in the middle of a loop. The second step is mu separation. In this step, the input curves will be separated into primary features and secondary features. We ensure that primary features are away from each other by a minimum distance mu, a user-controlled parameter, except they connected at the same point in a good angle. In later meshing steps, we will try to exactly preserve primary features. And now the right image only shows the primary features. As for the secondary features, which just showed up inside the circles and marked in green, after the domain is meshed, the edges associated with secondary features would have more freedom to move, and they will keep linear in the output. After the input constraints are properly marked, we first generate a linear mesh using similar strategy proposed in our last year's SIGGRAPH paper, Tetwald. Though Tetwald is an algorithm for 3D linear tetrahedralization, it can be easily extended to 2D triangulation. Since Tetwald is a pretty new algorithm to make today's talk self-contained, let me briefly explain the main idea of Tetwald in 2D. Tetwald takes a segment soup as input and produces a linear triangle mesh that conforms to or approximates the input within an epsilon envelope. The pipeline of Tetwald can be divided into two stages. The first stage generates a valid triangle mesh in rationals and exactly preserve the input. Note that in this stage, all computations are done in rationals. And the key step of this stage is BSP subdivision, that it uses the line of input segment to subdivide the domain and generate a convex polygonal mesh in rationals, which can then be easily triangulated. The second stage is mesh improvement. We use for-loop operations to optimize mesh quality. They are edge splitting, edge collapsing, phase swapping, and vertex smoothing. In this stage, we ensure all elements are valid, that is, non-inverted, and we ensure all boundaries are staying inside the epsilon envelope. As the mesh quality improves, we can then gradually round all rational coordinates into floating point. And in the end, we can get a valid high-quality output in floating point. Tetwald has been tested on 10,000 real-world models, and it achieves 100% success rate. Since Tetwald is robust, automatic, and can generate high-quality elements, we adapted into our algorithm Triwald with two main differences. The first difference is, besides the environment constraints on quality, envelope, and inversion of the original Tetwald, we add another environment constraint, that is feature environment constraint. This constraint first requires that all feature edges marked in red on the right have their associated curves having total curvature smaller than alpha. It's easy to understand that the smaller the alpha is, the easier the linear mesh can then be curved. But small alpha could also limit the movement of feature vertices. The constraint then requires that all feature vertices can only move along feature curves. Note that here I use feature to refer primary feature. As for the secondary feature, they can move inside the epsilon envelope. That is the same envelope used in test wild. The second difference is we add a vertex projection operation because we want all feature vertices to be on the feature curves. So we project them back to feature curves in every iteration of mesh improvement. After this step, we have a valid linear mesh with some curving part over-refined. And the last step is curved mesh improvement, which uses the same local operation as those used in linear mesh improvements, but on curved meshes. So in this step, we first need to curve all feature elements that are elements with primary feature edges, thickened in red on the right. If an element becomes inverted after being curved, we keep it linear and try curving it later. As for secondary feature edges, they will remain linear. Since the Jacobian of curved elements is not as constant as that of linear elements, so we used the method proposed in this paper to check the inversion of curved elements. So after this step, the over-refined parts are coarsened, and the primary feature are preserved and secondary feature are approximated inside the epsilon envelope. And in the end, we can get a valid, high-quality curved output with input curves preserved. Tri-wild is easy to use, and users only need to control 3 main parameters. We also provide nice default parameters, which has been tested on a large data set. The first 2 parameters are mu and epsilon. Mu is used in mu separation for separating primary features and secondary features. The epsilon is the maximum distance that secondary feature edges can deviate from the input. Now let me show you how mu and epsilon affect the output. Let's focus on the middle of this model, full of straight lines. Here I'm going to show the close-up of output using different parameters one by one. The x-axis is for epsilon, the y-axis is for mu. When both parameters are small, most input curves are preserved as primary feature, marked in red here, and the green secondary feature edges are close to the input. When enlarging mu only, more green edges show up, and less input curves are preserved as primary feature. And when enlarging epsilon only, most curves are preserved as primary feature, but the green secondary feature edges deviate further from the input. When both parameters are large, few input curves are preserved as primary feature, and the secondary feature edges can have more freedom to move. User can also control targeted edge lengths for generate a mesh in preferred resolution. When the targeted edge length gets smaller, the mesh gets finer. There are, of course, existing methods for generating curved triangle meshes, like MATLAB. The left is the output of MATLAB. The right is our output. In the zoom-in figure, we can find our mesh has better quality. And believe it or not, MATLAB can be easily broken by just move one of the circles a little bit. Can you notice any difference between the original input and the input that cause failure of MATLAB? No, maybe. Also, MATLAB can only mesh simple geometries like ellipses and polygons. Another popular method is GMSH. The left is the output of GMSH. The right is our output. GMSH is too sensitive to the artifacts in the input, so it over-refined random. And the output of GMSH contains 19 inverted elements, which makes it unusable in later simulation. This is because GMSH curves all boundary elements, no matter it's valid or not, and then try to untangle them later, which could fail. We also did a large-scale test for evaluating the robustness of tri-wild. Our input dataset contains around 20,000 real-world SVG images from the OpenClipArt website. Before talking about success rate, let me define the term success. The definition of success is if the method generates an output within 6 hours using less than 64 GB memory. Trials succeed on everything except one model due to a large input size. Maybe you're curious about the input of this only failure. Let me quickly show it. So this model is full of dots, and each dot is represented by a small square. And this is not the end of the image. Let's continue. Continue. Okay. This is the whole image. Okay, let's go back to our result. Here is the timing plot of all outputs. On average, trials can generate an output using less than 10 seconds. Our curved outputs are in high quality and analysis ready, so it can be directly used in simulation like diffusion curves. The left is the input curves, and the right is our curved output. We solve the PD on our curved output and on linear mesh in same resolution. By switching between the linear result and the curved result, it's clear to see that in the curved result, the colors are correctly diffused and the boundaries are more smooth. Here's another simulation application, inflation, which solves a bi-Laplacian equation. The left is our curved output, the middle is the simulation result using our output, and the right is simulation result using linear mesh in same resolution. If we switch between the curved result and the linear result, one can quickly find the difference, especially on the highlighted region. We also have an example for Stokes fluid simulation. We let the fluid go through a region full of holes, and in the close-up of output using our curved mesh, the white streamlines are symmetric and smooth, while in the linear output, the streamlines are not symmetric anymore. And it's easy to find difference by switching between the two results. Note that for all simulation examples, the simulation on our curved mesh only takes a little bit more time than the simulation on linear mesh in same resolution, which is negligible. We also performed an elasticity simulation example on our curved mesh and a dense linear mesh, which is regarded as ground truth. By comparing the middle image and the right image, we can find that our result is visually similar to the ground truth. However, the simulation on the dense linear mesh is 1,000 times slower than our coarse curved mesh. The linear mesh takes around 2 minutes, while our output only takes 0.1 seconds. So for all simulation examples, we use the library PolyFEM to solve the PDEs. We also have a pipeline for generating linear meshes as a byproduct. This is basically the implementation of test wallet in 2D, which achieves same robustness. We tested our linear pipeline on 3 datasets. The first dataset is a raw dataset, which contains the piecewise linear approximation of the 20K SVG images. The second dataset is the cleaned dataset, which is a raw dataset with duplication and degeneracy removed. The third dataset is the snapped dataset, which is a raw dataset with snap running. We compared our result with seagull and triangle, and here are success rates of all methods on 3 datasets. The definition of success here is if the method generates an output within 1 hour using less than 16 GB memory. Note that our linear pipeline uses way less resources than our curved pipeline, which requires 6 hours and 64 GB memory in maximum. When the dataset gets cleaned up, the overall success rate is increased, and here I highlighted the winner of each group. With enough resources given, our method can achieve 100% success rate. Note that 64 GB is not crazy. It can even be supported on a desktop computer. I'll skip the comparison on timing, mesh size, mesh quality.